Mic working? Okay, good. All right. Yeah, so I know you've heard a lot of stuff already about instruments and algorithms, and so what I'm going to focus on really here is how do the data, well, let me go to my purpose. So basically, how does the PACE science data make its way from, so we have instruments flying on a spacecraft to ultimately to, folks like you as in the form of scientifically, hopefully meaningful data products. And it's kind of a long, involved path. And if you're actually going to use the data, you actually don't need to understand it all, but I'm going to explain it to you as best I can. All right. So, for starters, we have to collect data. Of course, all of the instruments on PACE are visible up through shortwave IR, which means they only collect data in visible wavelengths. So we only bother to collect data, science data, when we're viewing the lit Earth. So this shows the cycle. I guess this is a pointer? Yep. Okay. And here it goes. All right. So basically, this is, of course, the sun shining on the lit side of the Earth. And instruments the orbit is from south to north on the lit side. So as the spacecraft comes over what we call the southern terminator crossing, we start collecting data. HARP starts a little bit early because they want to view the lit Earth through their entire range of forward and aft views. So they start back here when the most view starts to see the lit Earth. OCI and SPECS both turn on over the terminator. OCI at this point is tilted aft. You might have heard something about glint, so we tilt aft to avoid the sun glint. We go to the midpoint of the orbit. OCI then goes from aft to forward. Meanwhile, continuing to collect data, we go all the way up to the northern terminator. OCI and SPECS stop at that point. And HARP goes a little bit longer so that its aft view sees the full range of the lit Earth. We have marked here, the requirement is actually to 75 degrees solar zenith angle, because that's about where the limit of ocean color data is for OCI. So that's our requirement, but we're going to get it all anyway, because we can. And then on the aft side of the orbit, there's a number of things happening. For one thing, we have to move the tilt from forward back to aft, so we're ready to restart on the next orbit. HARP actually doesn't download its data through this interval, so they do it during the eclipse, and SPECS does some calibration and whatnot, but the data of interest are all collected in this half an orbit well over the lit Earth. Okay? By the way, feel free to jump in with questions at any point. Just raise your hand and I'll be happy to answer. All right, so this is a very simplified view of what happens on board. Most of the time, the spacecraft is not within view of a ground station. And I'll show you in another slide what ground stations we do see. But for the most part, we spend about 90% of the time out of view of any ground station. So the data have to be stored on board. So data from all three instruments send the data over SpaceWire to this data storage board. As I mentioned before, HARP actually waits until we're in eclipse in order to do that. OCI and SPECS1 do it in real time as it's collected. And in parallel, there's all of the spacecraft subsystems are also sending telemetry to a different part of data storage. So then what happens? We get to a station contact, and those last anywhere from about 5 to 10 minutes. So during that time, data on the data storage board are then sent to the RF communications system. There are two different transmitters. The KA band is the high rate transmitter, and that's where the science data goes down because the data volume of science is vastly greater than that of the telemetry. Telemetry goes by S band at a lower data rate. They each go out through dedicated antennas, and then with a bit of reformatting and converting to RF in between, and get transmitted out in the form of an RF signal. Yes?
What does KA band and S band mean?
I'm sorry?
What does KA band and S band actually mean?
They're frequencies.
Oh, okay.
And I don't know, don't ask me the frequencies, I don't know them off the top of my head, but we could easily look them up. But yeah, Ka band is a much higher frequency than S band, therefore can carry a much higher data rate. Yeah, these are all standard frequencies that are used by spacecraft to downlink data. Yes?
Is there any encryption when you're transmitting the signal?
I'm sorry.
Is there any encryption when you're transmitting the signal?
Encryption.
Say again? Oh, encryption. No, the data are not encrypted for downlink because our data are not, do not represent national security interests. The command data that are sent to the spacecraft are encrypted just because we don't want somebody else commanding our spacecraft, but no problem with the downlink. Good question, though. All right, so then we come within view of a ground station. And we use ground stations at Alaska, Svalbard, which is an island north of Norway, way up north. Just about nothing else goes on there except the ground station that I'm aware of. And then Punta Arenas, which of course is way down at the southern tip of South America. And we choose these locations on purpose because at high latitudes, spacecraft flies over them several times a day. So we get lots of station contacts. Ideally about one every orbit. We actually only need about 10 of them a day in order to get all of the data down. Wallops is only used for telemetry, S-band, Wallops Island, Virginia, which of course is on the Atlantic coast. So what happens? It looks like I'm missing some of my arrows here. I don't know why. I don't know quite what happened. All right, I'll just draw them in here. So the science data, I'm missing the science data arrow for some reason. It's not displaying. So science data gets downlinked from PACE to one of these stations on the Ka band, as I mentioned earlier. Then the data actually get sent to us by way of the cloud. And this is something new for NASA. Instead of a direct transmission link from the station to Goddard, they are now doing everything in the cloud. In this case, Amazon Web Services is going to be our data conduit. So the data are delivered to the cloud. They're reassembled into the files that were stored on board the spacecraft. And from that point, they are available to be pulled to the science data segment, which of course we operate at Goddard, and that's of course the group that I represent. In parallel with that, the telemetry are sent to the Mission Operations Center, who actually operates the spacecraft. They're the ones that are most interested in the spacecraft telemetry, but they also make the telemetry available to the science data segment. And of course, as part of the planning process, we provide plans and schedules to the MOC, which are then uplinked to the spacecraft also on S-band. So that's a real short description of how the data gets from the spacecraft to Goddard. Okay?
What would be the advantages of using a cloud service versus direct transmission?
To be honest, I had nothing to do with that decision. This was a decision that, there's an organization at NASA called the Near Earth Networks, which has been in the business of operating the ground stations and arranging to get the data from the stations to Goddard for as long as NASA's been in business. During the early development phase of PACE, they had started a program to convert that activity from essentially either leased or dedicated ground links to cloud-based. If you're asking me why, I can't actually answer that, but it was their decision and NASA's decision to make. So, okay, all right. Oh, okay. Now the arrows are showing up. I just had to click it again. And finally, the science data. Okay. For some reason, I didn't realize that this was actually going to happen. I borrowed this figure from somebody else. All right. So, what happens when it gets to Goddard? Well, we process the data through a number of what we call data product levels. And these are actually standardized across NASA Earth science missions. I'm just going to give a real quick description of each one here, but then I'm going to talk a little bit more about why do we do this. All right, so what we call level 0, which is basically the data, essentially what we are pulling from the cloud, is the level 0 files. And this is in the form of CCSDS packets. CCS, of course, is a consultative committee for space data systems. Nothing can be decided at NASA without a committee, so we have a committee for deciding what these packet format conventions are. And what we call level 1, which is at 3 different levels. First, we take the data out of the packets, put it back into a useful form, and I'll talk more about what that means in a minute. Then we calibrate and geolocate the data. Of course, calibration means converting it to physically from, it normally starts out as integer values, just counts. We convert that to physical units. Geolocation, of course, is where we figure out what the instrument was actually viewing, what locations for each data sample. Then finally, primarily because of the polarimeters, we have something called level 1C, where we take views of a given location that were taken at different times from different points of the orbit, and I'll explain more about that later. And then finally, we get to level 2, which is where we get into the real science. And level 3, we take the level 2 data and put it into a geographic reference frame. All of these other products are in an instrument-based reference frame. So we put it into a geographic frame and start to accumulate it over progressively longer time periods. And I'm going to describe these in more detail, so I would suggest if you have questions, hold on to them for the moment. I will say all the products above level 0 are in what we call NetCDF format. I don't know how familiar you are with that, but Network Common Data format, which is a platform-independent self-describing format that's widely used at NASA and elsewhere. Okay, so one thing that so you might well ask, why do we need all these product levels? Why can't we just go from the satellite data right to the science data products? Wouldn't that be much easier? Well, there's a good reason for breaking it up into steps. And I said, okay, so each data product actually represents a logical step in the data processing. I mean, it is a complex process, and there's a number of essentially independent decoupled steps that need to be performed to get from the satellite data in the packets to scientific data products. And it makes sense to break those up because it enables us to verify at each step along the way that we're doing the job correctly. Also, in some cases, there are steps that can only need to be performed once. So we save a product at that step, or there's products that branch off into many other directions, and so we have a product at that step and so on. So it makes sense to have this processing broken up and to save products or generate products at what we call these different levels. So starting with level 0. Okay, first of all, this is everything the satellite made. This is what we've paid. In the case of PACE, am I allowed to state the number? Close to $1 billion. Several $100 million to generate. So we're going to save this. every last bit of it is going to be saved. What we typically do is to store the data in multiple copies in different locations just to protect against data loss in one location. But all of the downstream product levels, if necessary, we can start again with the level 0 data and do it all forward again. So it's very important to save that. All right. Level 1A, the data are taken in a logical structure. In the case of a scanning instrument, a logical data unit would be one scan, or in this case, we say for OCI, one scan is one rotation of the telescope. So that is a set of data, a set of pixels, one line for all of the spectral bands. And so that's a logical unit of data. The packets aren't organized that way. The data are broken up into many, many packets. It actually takes close to 3,000 OCI CCSDS packets to make up one scan. So the first thing we want to do is take all those thousands of packets, put them into a data structure as the instrument originally generated it. So that's a very well contained step. For HARP and SPEX1, we have, misspelled there, they have detectors, arrays, and so a logical unit is one image of the detector array. And once again, the packets aren't broken up that way. It takes numerous packets for either one of those instruments to represent a single copy of the detector array.
Does every NASA mission have to tear up their data to make CCSD work?
Yes.
Okay.
Yes. The packets are often not large enough to contain an entire, logical unit of data.
As long as Webb has to do it too.
Yeah. Right. I mean, and the same is true for other instruments as well. And honestly, the way the data are broken up is very instrument specific, because each instrument has its own electronics and its own flight software. And so you can't necessarily say, okay, I know how to read a MODIS packet, so I know how to read an OCI packet. Sorry, not true. So everyone is different. So the first thing we want to do is put the data into a multidimensional structure that represents how it was collected by the instrument. And that's the job of level 1A. And so that's a good place to stop and say, have we done this right? Have we unpacked all the data correctly from the packets? At this point, we also go out and grab some additional data from the spacecraft, primarily use navigation data that we'll be using for later processing. Might also be some other telemetry of interest on the spacecraft. And this is also where the times are converted, again, from however they're stored in the packets into a useful format, which is usually a date and time of day. And finally, we normally process the data in what we call granules, where we say, we're going to chunk the data up n minutes at a time. For OCI, we're doing it 5 minutes at a time, and this is just to keep the file sizes within reason. The polarimeters have different granule sizes, but the granule size is set at level 1A, and that granule size is maintained all the way up through level 2. Okay. So, level 1B, this is where we start to do some heavy lifting. Calibration and geolocation. All right, well, first thing, of course, you want to convert the data. As I said, they normally come in the form of integer counts. So you have a scale factor or gain that converts them to physical units. It could be radiance or reflectance, or in the case of a thermal infrared sensor, which we don't have, it might be brightness, temperature, or something else. But the point is now you've got the data in actual physical units. But at that point, you're only just getting started, because instruments have all kinds of little quirks that affect the data. I mean, the response to an incoming signal may not be completely linear. In fact, it rarely is. So, in the case of a scanning instrument like OCI, the response may change from one end across the scan. In the case of an instrument with many detector elements, each detector element is going to have a slightly different response. So you've got to flat field the data, and so on. Temperature is another common variable. So all of these affect, in order to achieve the lowest possible uncertainty in the calibrated data, you have to take account of all of those effects, and that's all part of the level 1B processing. So every known instrument effect that we can develop a correction for is incorporated at level 1B. So it's a pretty hard job. A lot of these, most of these corrections are actually measured during pre-launch testing, and because they can't easily be evaluated on orbit. The one correction that is evaluated on orbit is how the response changes over time, what we call the temporal variation, because almost every instrument is not 100% stable over the life of the mission, and therefore you have to not only do the basic gain correction, but you have to see how that gain varies over time. So all of this is done at level 1A. Finally, we have this step we call geolocation, which is where we take the navigation information, which is the spacecraft position and orientation, and we combine that with an instrument geometric model to determine where every measurement of the instrument was looking on the Earth. And so that's also a job that has to be done very precisely, because we're talking about instruments with, in the case of OCI, 1 kilometer resolution at nadir. Some instruments, of course, are much higher than that. And this is another aspect that has to be monitored during the life of the mission to make sure there isn't any variability in the spacecraft pointing or instrument geometry over time. This is also where we incorporate information like the sensor and solar viewing angles that are used for downstream processing. Okay? And finally, level 1C, which actually our group is doing for the first time for PACE, because for the first time we're processing multi-angle data from the polarimeters. And in this case, we're taking observations of a given location that were taken at different times from the different viewing angles, and we're resorting the data, rearranging it so that all of the measurements of a given location at different times are collected and put in, and put together. And this is required for the polarimeter algorithms because they use the information about all the viewing angles for a given location as part of their science algorithms. Okay? Yes?
Already you are implementing L13 data products. Namely, you co-location and put everything together. How ready is the software?
Oh, actually, it's the grid development is in good shape. We're still working on the part of the software to take all of the instrument data and put them into the level 1C format. OCI, I think, is pretty much done. I think the work, there's still work in progress on both of the polarimeters for that. So yeah, it's not ready for prime time yet, but it's pretty far along. All right. Okay. All right. So here's a quick example of, what the difference between level 1B and level 1C for a multi-angle instrument. So at level 1B, we have the spacecraft in a given location at a point in time, and we have multiple views from the instrument at that time. And of course, they're all looking at different locations along the orbit track. And so that's our level 1B. By the time we get to level 1C, now we have identified all of the times and the points in the orbit when the instrument was looking at a single location on the ground. And so we're arranging the observations from essentially time-based to a geographic base. It's still referenced to the orbital track, but they're now all co-located in space instead of associated in time. Okay, and that's done for all the views. In the case of HARP, of course, there's a total of 90 different views, I think, that all have to be co-located. So, all right. Any questions about that? Okay. All right. So, going on to level 2, as I said before. Level 2, this is where what we really call the first science product. Everything up until that point, up through level 1B and even level 1C, is essentially engineering. It's the instrument design, it's the spacecraft, location and orientation and whatnot. So level 2 is where we start to incorporate the science. And of course, I imagine you've heard quite a bit already about what science products PACE will generate and some of the details of the algorithm. So I'm not going to talk about that again. The point is that this is, we know that this is where all of those algorithms begin to be applied, is at level 2. So we take the calibrated data and generate whatever set of parameters, and of course, there's a long list of parameters for PACE. We have the OCI level 2 products. We have separate products for the ocean color, aerosol, and cloud properties. We have level 2 products for both of the polarimeters. You've probably heard, but I'll say it again, part of this process normally requires additional data sources that are not generated by the instruments. We call these ancillary data. For example, meteorological fields like water vapor, surface pressure, there's a whole range. Ozone, we all get those from sources outside of the instrument, from other sources. Some of them are generated by other instruments. Some of them are done by incorporating instrument data into models. So we have to pull all of those data together as part of the level 2 processing. I would say in most cases, this retrieval is done at full instrument resolution. There are a few cases where instrument data are binned to a larger or coarser resolution to reduce the noise level as part of the retrieval process. So I won't say exclusively at instrument resolution. These are still in the instrument reference frame, which is to say along, following the orbit track. And then finally, we store quality flags, and there's a whole long list of those, and actually touch on those a bit later for the ocean color products. But those basically indicate a combination of any algorithm issues that were encountered, if there was some kind of an issue with atmospheric correction, for example, and also other conditions like geometric conditions, the sensor angles being out of the useful range, that kind of thing. So, okay. Finally, level 3 products is where we take the level 2 products and we normally start with spatial compositing by taking a day's worth of products, level 2 products for a day, and we put them onto a geographically oriented grid. So all level 3 products are on the same reference frame, which is separate from level 2. And then we temporally composite them over longer time periods. We go to, our typical periods are 8 days, 1 month, a season, a year, and then the entire mission. And I mentioned here, and I'll explain a little bit more about this. The coordinate systems are normally either equal area, which is how we generate what we call our bin products, or equal angle, which is what we do with our map products. Okay? All right. So here's just an example of, and this is actually for the VIR sensor on JPSS-1, but this is a comparison of level 1B versus level 2. Level 1B, we actually used 3 of the instrument bands, visible bands, to generate what we call a true color image. Of course, what level 1B really is however many bands the instrument generates, and a radiance at each one. But in terms of, getting an idea of what the data look like, the calibrated image looks like, we generate these true color images. And so you can pretty easily see, the clouds, the land, and then the open ocean. And then when we get to level 2, now we're in many cases excluding a lot of these data. So in this chlorophyll image, you can see, well, obviously, we're not doing it over the land, so that's represented in the brown. And all of these empty spaces, of course, correspond to the clouds. There's a lot of clouds. We lose a tremendous amount of data to clouds every day. Roughly 2/3 of our data is clouded over. Can't help that. But anyway, so that gives you the sense of what happens between level 1B and level 2. If this was a different product, an aerosol product or a cloud product, of course, now you'd be getting a completely different set of areas. Yes?
I'm curious why do you have it labeled quasi true color?
It doesn't actually look exactly like what you would see, with your eye. That's why we call it quasi. I mean, we're taking a few discrete spectral bands, and from it we're approximating a true color image. I mean, the eye, of course, sees the full spectrum. So if you were actually sitting on the satellite, it wouldn't exactly look like that. It's just it's the best we can do. That's all. Yes.
Does that mean there is no true color? Is there actually a true color image with your definition when you say we can only take a couple of spectral bands, so we have to call it quasi-true color?
Right. Yeah. I mean, again, it's just a representative image of the radiances that combining data from, in this case, 3 spectral bands. So. Hope I've answered the question. I mean, this is done as a way of allowing people to select images for their own purposes. It's not a science data product per se. I mean, there are actually some other programs that generate what they call image products, but we're more interested in getting to the science. So this is really more of just a convenience than than anything else. Okay. So level 3 binning versus mapping. Sometimes people want to know, well, what's the difference? Why do you do both? Okay, so the first step in the level 3 processing is what we call binning. And in this step, we take all of the products for a given time range. As I mentioned earlier, we normally take a day's worth of level 2 products, and we remap them onto a defined grid. Now, for our binning projection, as I mentioned, it's an equal area projection. We use a sinusoidal projection, which I'll show you in a second. And one of the important steps is that we don't use all of the data. I mean, you saw in that previous image how much data actually contained chlorophyll. So all of those data that were clouded or land or whatever are actually excluded from the level 3 image. And we do that using the quality flags that were stored with the level 2 data. And so, I'll actually show you an interesting example of that in a bit, of how much data we lose to level 2 flags. Also, the most common bin resolution for our products is 4.6 kilometers. That just happens to be a convenient number because it's, you know, one degree of arc on the surface of the Earth divided by 24. So it turns out to be a nice round number in terms of the number of bins. Okay, so then once we generate a bin product, we then map the product to a standard projection. And our standard map projection is what we call equal rectangular or plat carré. I'm probably not saying that right. It literally stands for a flat, you know, projection in French. This is the product that most people request, and this is the one the modelers like best because most of their models run in the same reference frame. It's also an easy product to look at, you know, frankly. You know, it looks like a map of the Earth. So this is my own take on it. Binning is collection and selection, while mapping is projection. So that's my way of simplifying the difference, okay? All right, this is our equal area projection. As we mentioned, it's sinusoidal, and so in order to maintain a very nearly equal area, we vary the number of bins. These are latitudinally based rows, equal increments of latitude. By the way, this is much coarser resolution than our actual products because if we were to show the actual bin resolution on here, you wouldn't be able to see actual bins. But this is just a representation of our equal area projection. So we start out with an exact number of bins at the equator, and then as we go north and south, we progressively reduce the number of bins in each row to maintain equal area. Okay, here's an example, what we start with when we do a daily level 3 product. And this, I'm just arbitrarily picked, you know, 486 nanometer RRS. Again, this is from one of our existing missions. And what this shows is, first of all, because we exclude data where the sensor viewing angle was beyond a limit, in this case 60 degrees, there are inter-orbit gaps. So you can see these wedges in between the orbits. In addition, this is a nadir pointing sensor, so these odd-shaped missing areas here are where we excluded the data for glint. A nadir pointing sensor over the ocean sees a lot of glint. So we end up throwing a lot of that data away from our level 3 products. And of course, you can see where the clouds were, obviously the land masses, and the data only go up to 70, the number I mentioned earlier, 75 degrees solar zenith angle, north and south. So it doesn't cover the complete map. So basically, this is the result of saying, okay, we're going to exclude level 2 products, level 2 parameters based on a defined set of flags, and in a day's worth of data, this is what we have left, okay? And then as we composite, I'm sorry, is there a question? Okay, as we composite the data over a longer time period, so this is what it looks, I'm sorry?
Sorry, there was a question.
Oh, was there a question? I'm sorry.
That's just one satellite. That's like Modis image or something.
I think actually I used VIIRS,
Okay.
but this is what the product looked like by the time we get to a month's worth of data. So you can see it has filled in quite a bit. There are still some areas where we have persistent clouds. In this case, there's dust coming off the Sahara. That just keeps going. So unfortunately, that doesn't fill in after a month, and so on. You know, farther north and south, you can see there are more prevalent cloudy areas, but it's pretty well filled in by this time. But it does take a while with all of those data we're excluding to fill it in. Yes?
When does that overlap? What's the value that
Where we overlap, wherever we have multiple observations in a bin, we're just averaging the observations together. So if the orbit overlaps, we collect, you know, over a bin, we collect all the observations from the orbits that overlap, and we average them together. Yes?
So if I understand it correctly, the spin is the resolution of a rectangle degree by degree, or it's just kilometer by kilometer from the binning process. So I'm just curious, like when you're doing the collection and the average,
Yes.
is that collecting the data in a grid, like 1 degree by 1 degree?
Well, no. Our bins are 4.6 kilometers on the side.
And so it's not like
Not yet, no, we're still doing the equal area bin gridding at this point. And then when we go, once we've generated a bin product, we then we reproject it onto, you know, a rectangular coordinate system to generate the map products.
One like degree by degree, or it's still
No, it's still at 4.6 kilometers. Yeah, I mean, it would look pretty blocky if we were to do this even at 1 degree. So yeah, we maintain the binning resolution even when we go to the map products. Okay.
Thank you.
Sure. Okay. Sometimes people ask us, you know, why are we using NetCDF? You know, we've gotten emails from people that said, I tried to read one of your products into, you know, Excel or Word and it didn't work. But seriously, NetCDF, as I mentioned earlier, it's platform-independent, self-describing data format. So platform independence, of course, means, you know, it doesn't matter what kind of computer, you know, big endian, little endian, whatever, the product was generated on. Once it gets written out to a NetCDF file, you can read it out on any machine that is supported by NetCDF, which I think is just about anything. Self-describing means you don't need, in theory, you don't need a separate source of you know, documentation in order to understand the data format, and you don't need to understand the inner structure of the file. What you do need to do is use, of course, NetCDF, you know, tools or an API in order to read the file. Fortunately, those are supported, again, across many platforms and by a number of widely used tools like MATLAB and IDL and Python all have, you know, as well as, of course, C and Fortran, all have well-established interfaces to NetCDF. Another interesting thing, useful thing about NetCDF is that it supports what we call attributes, which allow the file, the product to be described at various levels. You can have attributes at the file level, at the group, because you can establish logical groupings within a file. So you can have attributes at the group level, and finally at the parameter level. And that's very useful because essentially you can include internal documentation in the file, and I'll show you an example of that in a second. Another useful feature is that it supports internal compression. So you can actually compress the data as they're being written to the file, and then as the data are read out, they'll automatically decompress. You don't have to worry about, you know, running, you know, gzip or something like that. It does require, again, standard tools or libraries, but it's widely supported. Okay, so here's an example of attributes attached to a specific parameter, in this case chlorophyll. So there are some standard attributes that are used for pretty much across the board. We almost always have a long name, units, a fill value for any missing values in the file, and then the valid min and max. There's also a standard name, which I believe is defined by EOS or ESDIS. Anyway, it's a standard reference to the type of parameter being stored in the file, which is separate from the long name. And then finally, you can make up your own. Honestly, I mean, attribute, you can call it, you can add an attribute, can be anything you want in addition to the standard ones. So we have a reference here. In this case, this is a reference to an actual publication. So this file actually tells you where the algorithm was published that was used to generate this parameter, which is a pretty useful thing. So when we say self-describing, we really mean, we think these products are self-describing. Hopefully they tell you a lot of what you need to know. I mean, obviously, you know, you probably need to, you need to dig out the publication if you want to know what the algorithm was, but at least it tells you, it gives you a pointer. Okay? All right. I said I was going to say something a little bit more about quality flags. I'm using this as an example of a group attribute. So we have, in this case, in our level 2 ocean color product, we have a set of group attributes which are the percentage of data that was lost to every quality flag, for which every quality flag was set. And so let me call attention, for example, to cloud ice. Anything that was flagged, and we essentially have one flag that flags the data for either clouds or ice, because for ocean color it doesn't matter. We can't use either one. And you can see 63.6%. That's how much data we lost in that granule to just clouds and ice. You know, we have a land flag. That's another 30%. And then we have a whole high glint flag, almost 17%, moderate glint, 43%, and so on. And then the number of other fraud fail is a combination of all of the flags that basically prevent us from, in this case, retrieving ocean color for that pixel or for that file. Yes?
So if we order data from NASA Ocean Color and we get that CDF file, but it gives you the option to select your region size, would the percentages automatically be built into your crop size when they give you the order of the file?
That's a great question. I don't know the answer. You mean if you subset the file, are the percentages recomputed? I'll be honest and say I don't know the answer to that. We'd have to come up with that for you. I mean, it would make sense, but yes, I don't know. Yes, ma'am.
Oh, I think this is only level 2.
This is a level 2 set of level 2 flags. But I think what you're asking is if you request a subsetted level 2 file, are these recomputed? I don't know. That would make a lot of sense, but I'll have to go ask somebody because I honestly don't know the answer.
It seems to be something you should be careful of, I guess.
Well, I think in practical terms, what often happens is that you'll download the whole granule, and so those values are correct. And then when you start to manipulate the data in your image software through, however you're manipulating it in CDAS, for example, that CDAS, as one example, CDAS is open source software that is used frequently. We're going to talk about that. That those numbers, like you can get the values for just your small piece because CDAS will tell you what that is. But
Well, I think what Riley was asking is, I'll show you, but on the ordering form,
oh, okay. I
you
haven't
have to get the
used
full
it that way.
file, you can actually get
Right.
a chunk of it if you
Okay.
wanted to go for a region. So
I
on
just
our
learned
end,
something new. Yeah,
Yeah.
it's smaller,
right.
yeah. Those,
Do those
Yeah.
transfer-
awesome if they were recalculated, but you're right. after
Yeah,
the fact,
I honestly, off the top of my head, I don't know the answer, but we can try to find out. I mean, we work with the people who do this, so we can certainly find out. It's, yeah. Okay. Yes.
So this, some of them we can guess what does they mean.
Yeah.
Some is hard to guess. Do you have a longer description of these attributes?
There is documentation which describes in detail how each one of these is calculated on our website. So, yes.
Will there be new flags produced with case that we should be sensitive to or aware of now?
I'm sorry, I didn't quite.
Are there any new types of flags that come up with products for the case data?
Will there be new flags for price?
Are we going to add to this list or change them for OCR?
Oh, we've been this for the ocean. This is the ocean color flag set. I mean, we have pretty much settled on this, I think, for quite some time. So we.
We would only add to the list, like, we've developed an optically shallow water flag that will be added to this. Right now, I think it's coastal zone. That might be it, everything we've done to date is like a geometric depth, like 50 meters is called coastal zone, but,
Yeah. I mean, yes.
optical depth, everything that matters.
Yeah, I mean, it's always a possibility, we've been working on these for, 30 years now, getting this set of flags defined, so
They get added every once in a
it's
while.
pretty, yeah.
Rarely.
Yeah. Yes,
Is there some minimum amount that you need before you would not report it in the bin data?
actually, the way the bin exclusions are set, it lists the flags for which data will be excluded from the bin file. So it's not done because remember, a bin is 4.6 kilometers on a side, and it can contain one or, several level 2 observations. And each level 2 observation has these flags set, either, and at that level, it's a binary. setting. So the way they're excluded from the level 3 product is when we generate the product, we give the software a list of flags that says exclude the data based on those flags, and then at each individual pixel, it is chosen or excluded based on whether those flags are set. I guess I didn't really explain that, but that's the way it works. Yeah, this is just a summary for the entire file, but we actually do look at these on a pixel by pixel basis.
And I can show you after they're online, we do have a website that
Right.
gives the long name for all of these and then describes whether it's masked or not.
Yeah.
I can follow up.
Yeah, I mean, I could have provided more details of this, but I mean, it was more using this as an example of what's in the file than a description of the flags themselves. But I understand the flags are a subject of some interest, so. Okay, any other questions about this? Okay. All right. We've been generating simulated paste data, and we've been using proxy data to test out the algorithms. People are interested in this, so we actually are well underway now in simulating data for all 3 instruments, at various levels of fidelity. I mean, simulating data realistically is a really hard thing to do. I mean, simulating the physical world is a daunting job, actually. And so we probably never get it, perfectly. In fact, we never get it perfectly. The point is, we just want to do it well enough to exercise the algorithms and convince ourselves that we're working. If we want to test the algorithms out on actual data, we will normally use proxy data from an existing instrument. And so both of those are very useful. We have something we call PyToast, top of the atmosphere simulation tool in Python. And so we've been using that to generate large amounts of simulated data at level 1B. We also have been working with a group called the Global Modeling and Assimilation Office to do a much higher fidelity simulation. So we've got a small amount of data that was generated by that group. And then both the UMBC and SFRON have been doing planning their own simulation activities for HARP2 and SPEX1. And we actually haven't gotten those data. We've gotten a few samples of those data sets yet, but we're really just getting started with those. What we have done is to plan for what we call a day in the life test using a defined date, in this case, March 22nd of this year. We're going to get a day's worth of data, simulated data from all 3 instruments, and run it through SDS altogether. And once we've decided that that's working, then we'll probably try to do it for longer time periods as well. Yes?
Just to add to that list, Jeremy, we talk about generating synthetic data based on my linear transfer model. I do have a set of simulation data using the same format as the OCI data format. And if you folks want to test with it, then feel free to contact me. And
Yes.
I hope maybe it's a mechanism to put that data to
Yeah, I should have. I didn't think about your efforts as well in this area, but yes. Okay. So anyway, so we've been working with all 3 teams. We gave them simulated spacecraft navigation, so they can all use the spacecraft, at the same time, looking in the same direction, and so on. We've done some previous simulations on earlier dates, but this is the first attempt we've made to do a common date for all 3 instruments. There's also been extensive use of data from precursor instruments to test out the algorithm. For example, for the polarimeters, we have the airborne campaign for both HARP and SPEX, and also there's the HARP CubeSat and so on. I've used a number of different data sources for OCI as proxy data. So there's been a lot of work going on in this area. And we have access to it on our website. This is our Ocean Color website. And I give the URL here, but if you go to the mission PACE, there's a link for simulated and proxy data. So as we make data sets available, they'll be posted on that website. You can see right here, for example, there's a link for the PyToast simulation. There's some SPEX1 simulated data already available. So we'll continue to expand access to the simulation and data as we generate it. Okay? Okay, and this is just an example. So we took this is actually not the latest version of the PyToast data. This is one version removed because we haven't finished processing the latest update yet. But this is basically what we got computing a day's worth of chlorophyll for the test data date from our PyToast simulation. So it looks pretty decent. It looks like chlorophyll. Okay, and that's it.